Okay, on to number 2 from our study guide for option B. They say a nuclear power plant can be modeled as a heat engine. A heat engine, that means you've got some system, maybe it's a gas, and you transfer heat to it. We call that Q in or Q hot. Why do we call it Q hot? Because that heat is coming from something hot. And then the gas does work as it travels toward a colder reservoir. Heat flows from hot to cold, right? Well, we're going to make it flow, and as it goes, it's going to do some work. Maybe it flows this way and it spins a pinwheel as it goes. And now the gas is over here, and at this point, the gas gives off some heat. We call that Q out or Q cold. Why do we call it Q cold? Well, because there is, some ice. There are ice cubes over here. Beautiful rendition of ice cubes. And so if you bring your gas into contact with a cold object, then heat will be given off from the gas to the cold object. So one of these values is positive and one is negative. Which is positive? Q hot, because that's heat transferred to the gas from the hot object. What's negative? Q cold, because that's heat transferred out of the gas to the cold object. We don't call these objects though, we call them cold and hot reservoirs. That's our fancy name, reservoir. Okay, calculate the Carnot efficiency. Oh, that's easy. We use the equation, which is it? T hot, T cold. Make sure you check the equation and do this yourself. Go look in your data book. Make sure you know where you find that equation, because it might be necessary for a test. Okay, this is the perfect ideal efficiency. Nothing is quite this perfect. And what's part B saying? Oh, it's saying, why isn't the nuclear power plant this perfect? Why doesn't it get all the way up to this perfect ideal temperature? By the way, before we move on, this is wrong. I just made a mistake, and look, I just made the same mistake again. What's my mistake? The equation is not theta hot, cold over theta hot. What's the difference between theta and capital T? Theta is Celsius, T is Kelvin. Do not forget to plug in the Kelvin value. Convert this to Kelvin before you start. Or, by doing this. Don't make the same fatal mistake that I made. Okay, and it's not Celsius anymore. At this point, when we add, it's Kelvin. You'll get a different answer, right? Just like 1/2 is not equal to, well, if you just add the same amount to the numerator and the denominator, right, you get 5/6. That's much bigger than 1/2. They're not equal. Okay, so explain why a nuclear power plant cannot reach the efficiency calculated in A. Well, because this is the best it can get. This is an ideal, perfect formula. In reality, nuclear power plants have other things that cause loss, like friction is the big one. Friction. And we'll just leave it at that for now. Okay, the power plant works, and by the way, if you do this calculation, what do we get? This is gonna be 349 plus 273. Okay, over 612 plus 273 equals -1. Oh, I'm doing it backwards. So it's positive this. 29.7. That's our efficiency. The nuclear power plant works at 71% of the Carnot efficiency. Okay, so let me just go ahead and say the efficiency is 71% of means times of 29.7%. So here's how I write that. And let me go ahead and just calculate the value times 0.71. Okay, so 0.21 0.099 or 21.99%. The power produced, and this is not super clear, this is supposed to be the electrical power produced, is 1.33 gigawatts. Electrical, is that the input that goes into the power station or the output? Electrical is the output. That's what we try to generate. Calculate how much waste thermal energy, that's our fancy word we'll sometimes use for heat energy, is released per hour. Okay, let me give you a hypothetical new question. You have your own power plant. You say, forget this. I'm going to make my own power plant that runs off your fuel, the fuel of you, right? And the efficiency of your power plant is 60%. Way better than that 29% or whatever it was. What was it? 21%. Way better. You are better than nuclear power. And you've got 60% efficiency. Your power output, ready for it? 100 gigawatts. That is a lot. No, let's make that your input. That's your power input. That's how much goes into your power station. What do you get out? You tell me. Your input is 100. You're 60% efficient, so you get out 60 gigawatts. So what's the wasted energy? What's the rate? Power is the rate. So what's the rate at which we waste energy? Well, it would just be 40 watts, right? And how did I get the rate of wasted energy? I took the difference. The input, that's your total. Some of it is useful output, and some of the input turns into just wasted heat. This is like the total value, 100. So before we can find the amount of thermal energy released per hour, we need to be able to take a difference. So we need both the input and also the output. Okay? Right now, we only have the output. So let's go find the input, and then we'll take the difference. All right, I plug in my value, 0.21099. I do know the power output. That's the 1.33 gigawatts. The input I need, so I can take a difference. I multiply both sides by Pn, and then I divide both sides by the 0.21099. And let me do this backwards again. 4.739 positive gigawatts. So now let's find the rate at which energy is wasted. And remember, we said take the total, subtract the useful output, out. Phonetic. Subtract the output, and what do we have? Well, we start with an input of 4.739 gigawatts, subtract 1.33, and the rate at which we waste power is, I'm doing all these backwards because my sign is off, 3.409 gigawatts. Okay. So now we know the power. We're looking for energy. How is power related to energy? Oh, power is the rate at which energy is transformed. Or you could put work in the numerator. Or maybe we'll put the heat energy. You could put anything you want. I guess technically we're talking about heat energy, aren't we? So I should probably put Q. And we want the wasted heat. So let me plug in the rate at which heat is wasted. We know this value, it's the 3.409 times 10 to the 9. The time, we know the time, it's 1 hour, which of course is 60 times 60 seconds. Make sure you plug in with seconds, and make sure you convert the giga, get rid of the giga. This is 3.409 times 10 to the 9. and then you just calculate the unknown. Finally, part D. Part D says, discuss the production of waste heat by the power plant with reference to the first law and second law of thermodynamics. Now, this is very vague, but we know we have to use the first law and also the second law. What does the second law say? Well, look, you see how we have Q in here? The second law, when we're talking about heat engines, the second law states that the input work, some of it turns into useful output. I'm sorry, the input work, the input heat, what am I saying? The input heat, some turns into useful output, and the rest turns into wasted heat, right? That's the second law when we express it using the heat engine form. Is that Clausius? Is that Kelvin? Which one is that? That's for you to go study up on. Remember, you have to know those forms, be able to state the second law, kind of word for word, the way we practiced. Okay, so how do we do this? Well, let's consider this. Well, let's start at that second statement. When we put heat energy into what's our gas? When we're talking about a nuclear power plant, we give this to the coolant, right? That's the stuff that heats up because it's near the fuel rods. Here are the fuel rods. Here's the coolant surrounding it. And then the coolant travels through this heat exchanger, right? And then it kind of pumps back in, and it spins a turbine. You know, there's a bunch of other stuff happening. I'm missing things in my picture. But the coolant is what heats up because it's contacting the rods, and then it does work. It spins the turbine, and then it cools off. So we transfer heat to the coolant, but only some of that heat does useful work, and the rest becomes degraded energy. It becomes wasted heat energy. But that's the second law. But the first law of thermodynamics says the total Q is equal to the total work plus the total change in internal energy. But if you have a cycle, then by definition, if it's cyclic, doesn't matter what the cycle looks like. Maybe it's like this. This is kind of the Carnot cycle. If you end and start at the same place, at the same temperature and pressure and volume, then there is no change in internal energy. Internal energy is 3/2 nRT, right? Or 3/2 PV, we could say. So if you end at the same temperature as you start at, there is no change. What does that mean for us? Well, let's look at this left side here. The total work is the input minus the output, right? But this and this say the same thing. We can start at, we started out in blue. Oh, blue. Come on. We started out with the first law of thermodynamics. And then we said there is no delta U. We applied it for the entire cycle. And then by the time we got down to here and plugged in for the total heat, in a heat engine, the total heat, there's some input and there's some output. So in this process, we transformed from the first law of thermodynamics to the second law. So to see how this all fits together, read the key. This is not a complete explanation. It's just sort of explaining the logic behind the explanation in the key.